Our next talk is a short one. It's a short talk by Youngmin Kim, who is here. He's going to talk about benchmarking safe optimization algorithms.
Hello, my name is Youngmin Kim from Alliance Master's Business School, and today I'll present benchmarking safe optimization algorithms. To talk about the safe optimization, we should talk about the typical optimization problem. So in typical optimization problem, you want to optimize an objective function. So you want to find an optimal input point efficiently, which is a solution, policy, strategy, or decision, where objective function represents reward, efficiency, or cost. But in safe optimization problems, you have some constraints related to safety. For example, imagine for an engine calibration problem, you would like to ensure the heat and pressure is below a certain threshold, for example. And for the movie recommender system, customer dissatisfaction, pain level for clinical experiments, and non-computability for the simulation study. So such constraints are called safety constraints, and the H on the right-hand side of the equations are called safety threshold. So the thing is, what is the main difference between standard constraints and safety constraints? Usually, standard constraints can be violated. You can just find that, oh, it is not feasible, like for example. However, as you see, if you violate safety constraints, it results in like irrevocable consequences like engine breakage, customer loss. So in safe optimization, now the goal is optimizing an objective function while not violating the safety constraints. So formally, we have an object that we would like to maximize the noisy objective function with the noise from the Gaussian distribution. And we will face some, let's say, K safety constraints here, where X is an input point for D input variables from X1 to XD, with bounds on each decision variable, where the D is defined by feasibility constraints. There exist two algorithmic branches in safe optimization. One is through evolutionary algorithms, and one is through Bayesian optimization. So basically, evolutionary algorithms are population-based heuristic, and by default, they apply to safety constraints. However, for example, safe EA, it rejects any solution if nearest neighbor was unsafe, for example. As I said, safe GP relies on Gaussian process regression. For example, if you see the plus above, you'll see how Gaussian process is regressed based on the past observations and how the safe optimization algorithm would work with the observations, for example, in the plus below. We just adapted two tables from our previous research, which was on the literature review on the safe learning and optimization algorithms. Here, we just show there are many algorithms related to safety problem, and we emphasize that in optimization problem, there is an EA called VA, which can be augmented onto any EA. And one other important algorithm is SafeOpt in SafeGP, because it inspired many other safe optimization algorithms, which constitute the largest body in the safe optimization study. Yeah, these show their properties. Yep. So the current issue is that there is no unified guidelines for benchmarking both sides of algorithmic branches. And also there are some parameters that can potentially have some impacts on the algorithm performances, but there was no investigation. And there's lack of information, for example, which algorithms to use which problem. For example, for the unimodal function, multimodal function, would it be same? So research proposed benchmark guidelines and tools for the fair benchmarking of both sides of algorithmic branches. So if we start from the typical benchmark suite, you will fix the dimension and you have the objective function, and you create problem instances to repeat the algorithm to average the algorithm performances. And then you have a quality indicator. However, you can see they allow many evaluation budget, and they fit the performances in the target values. However, in our study, we create problem instances by providing different locations of initial safe seeds. And we use quality indicator as noiseless BSF because we only allow 100 total evaluation due to the expensive nature of safe optimization. And we remove the target method because we want to also observe whether they are able to perform global optimization. So we will change in our study location of initial safe seed. And initial safe seed means the input points already known as safe for the algorithm initializations, and number of initial safe seed, level of safety threshold, and budget of unsafe evaluations. And here is two objective functions we use for our experiments: unimodal sphere function and sibling length function. If you see the lines inside the circle, they are safe regions. And you will see that there is an isolated local optima regardless of the level of H. And there are two local optima which are not isolated if the safety threshold is low, but isolated if it's high. So there's a scenario we will only sample the ISS from the local optimum 1. This is scenario 1, or either from local optimum 2 or 3. This is scenario 2, or from both, like a difficulty of the problem. So the result is that if we provide more initial safe seed, we found that the algorithms, which is in the above, they show quicker convergence and they show robust optimization. For example, you can see the decreased size of the standard error around the mean function, and reach to better BSF and also less unsafe evaluations in the plus below. And we also we just observed that only one safe EA and only one safe GP perform global optimization. And here is the safe EA, which is a VA, requires diversity of samples. It only performs global optimization in scenario 3. And safe GP requires connectivity. If the safety threshold level increases and the safe regions are disconnected, they don't perform global optimization. For example, here you can see how VA move towards around the global optimum, how safe op stuck at how an algorithm stuck at a certain point, how an algorithm just perform local optimization, and how another safe UCB algorithm just stuck, and how modified safe UCB performs our global optimization. So can we expect perfect safety? Theoretically, they guarantee safety. However, in the problems, assuming the real world application, hardly yes. And we should think about trade-off between objective function value and unsafe evaluations. And so these impacts of such parameters remained hidden before our study. So definitely there is need for further investigation of such parameters. And future research is development of more efficient algorithms and how to make our current algorithms more efficient, and understanding the properties of the real-world safe optimization problems, and formulate and investigate other types of safety constraints. This is all, and thank you for listening.